The idea of this work is to try to be able to program over low-level data in a high-level language like Orthodox. And there's a lot of existing work on programming in low-level languages like C, for instance, and then importing it in a proof assistant and using, for instance, separation logic to prove that the program is correct. But the idea here is to use a correct by construction approach so that you're not writing the program first and then trying to prove it's correct, finding a bug, fixing it, going back to your proof, finding another bug, and so on. So you want to write things correctly from the get-go by having strong specifications and then slowly building your program in a way that respects the specification. So to get an idea of what it is that you want to do, we can start with a small language. So let's say that we have some terms, and we just have one construct, which is dereferencing, and it takes a label, so we have an infinite number of labels. And so what this command will say is that if I have a memory location, well, a label for a memory location, I can dereference it and I will get access to it. So then if you want to try to prove the properties of these type of programs, you end up with something that looks a bit like or triples. And so you can say something like this. Well, assuming that L points to some value W, for instance, the result of deref of L will be a value which I know will be equal to W. So the syntax is where here at the top you have your assumptions about the ongoing state, the current state of the system. Here you have the program you're interested in, and here you bind the value that the program returns, and then you have an assumption about the state of the system. Actually, here you probably want to say that it is still true that L points to W. Otherwise, if you dereference twice in a row, the second time you won't be able to say what it is that you should get.
Those separation logics we have to be separated.
Yeah, so that's the point. But so at the moment we only have dereferencing, right? Which makes everything fairly easy. The state is read-only basically, and so there are. That's a hugely simplifying assumption because you know for a fact that everything that was true here can stay true afterwards. In particular, you can prove a really strong, or you can add a really strong principle to your system and say that if I am able to prove something, maybe. Okay, so let's say that this is your axiom for dereferencing, and then you would have a weakening axiom saying that if from P running P, you can compute Q, then you can just weaken it by any extra assumption on the right-hand side. So that you can prove something about a program that only dereferences one label, and then combine it with smaller proofs about programs that talk about other state locations by just embedding the extra assumptions in the assumptions and getting them by specification. So this allows you to do your proofs on program fragments in the smallest possible set of assumptions about the state of the system, and then combine them to talk about bigger systems, that is more things. But then you can start getting trouble if you want to add something that says that you can also assign. So let's say I have an assign thing that takes a label and a value. And so here, what you would like to write as the axiom for assign is something like this. I guess we don't care about the assumptions, like you don't need anything. And if you assign L to, I don't know, 2, or actually an arbitrary value, then you get something back from these, like a unit or whatever. And now you know that you have this assumption. L points to the value that you used here. And this is how you can specify the fact that this will actually modify the memory to allocate the value. But then if you combine these two things, you can get in trouble. Because if you take your R, simply L points to 0, and then the value to be 1, you can see that here you'll start from L points to 0, and you'll end up with L points to 1 and L points to 0. And from that, you can conclude anything. This is just possible. So this is where in separation logic, instead of having the conjunction, the normal logical conjunction here, you have a notion that's called the separating conjunction, which states that basically P and R are talking about different subsets of labels. And so they're talking about different parts of the memory, which means that it's safe to combine the two assumptions here. So here you wouldn't be able to recombine L points to 0 because L is already mentioned in the conclusion here. And so you regain the ability to start talking about small programs in isolation and then combine the results when you're combining the programs to a bigger space. Yeah.
You could see even if you replace the ands and middle with stars,
Yeah.
your assign rule is wrong. Because you can still apply it and still get L points to 1.
Well, no, because I mean this is unit, right? But unit for a certain set of labels.
You need to write there that L is the location which points to something.
Yeah. Yeah, so implicitly here you're actually at top, and then all the predicates need to come with a set of labels they're talking about, right? More.
I think the usual assignment rule says L points to, well, there exists a B prime, such that L points to B prime.
Oh, yeah, I guess you can do it like that, but there's no information.
There is.
It's already.
There's the fact that the footprint black line.
Right, it's already allocated. So.
That, no, there's two bits of information that are conveyed in the separation of exertion. One is what's true, and the other thing is what is it true about?
Yeah.
And that's the footprint of that thing. So that existential is then saying, okay, I don't know what's in that cell, but I do have access to that cell.
Oh yeah, okay, I see. Whereas you wouldn't be able to write that program if L didn't belong to you already. Yeah, so I mean you could have see this is as a shortcut.
Point is that you can still apply the favorable.
Yeah.
But the precondition is then inconsistent, so you can't never have to talk about precondition.
Yeah, yeah.
But you can still state the bad post condition that L applies to 0 and L applies to 1.
Yeah, I guess it depends whether you're checking that the predicates make sense, or whether you're encoding it in a way that it just degenerates to something that's basically the empty predicates. If there's a class.
Well, if you're doing it entirely syntactically, you can't. You don't know.
Yeah, I mean, it's yeah.
No, mine was about frame rule, whether
Yeah,
were you
the weakening.
if you want. Well, I would was frame rule, you say weak.
Yeah.
Okay, fair enough.
I would put a weakening because it's weakening would be if you just did it to the precondition. It's because it's
Sure, you're wrong.
Right. So so then the point of this work is to try to take this sort of logic, but instead of having a deep embedding, which is what a lot of people do, where they actually describe the deduction rules, you have more of lightweight. It's not even a shallow one because it's it's not actually implementing these rules, but it's implementing a system with restrictions that are inspired by these rules and allow you to then manipulate explicitly the content of the memory. So that's when I start sharing screen. So let's see this goes. Yeah. Right, so the first thing is that instead of having sets of labels, which are, and sets are always a bit annoying to manipulate and so on, we have this notion of region. And the idea is that it's a region in memory that contains some data you can talk about. And this is just an alias around a buffer. And it's not publicly exported, which means that the client can never open regions. So they're completely abstract. They cannot compare them for equality. They cannot inspect their content, which means that there shouldn't be any way for the clients to then violate all of the invariants that we're going to enforce through the types by actually poking at the data directly and making observations. Yeah.
Yeah, I was gonna say, really too deep into this. Have you looked at Arjan's work in CPP 2019 on doing separation logic and session types?
Yeah. So I've read this thesis, and this is more of a deep embedding of separation logic. And then you have to explicitly manipulate the proofs and so on. And it's really eye-opening in terms of the work you can do. It's really important. But here I'm trying to avoid manipulating single proofs. And then the idea is that we're gonna, instead of saying, well, I guess as Bob was saying here, we should have there exists an L, B, whatever such that L needs to be. This is a way to say that you own the location L, and so therefore you're able to manipulate it because you know for a fact that it exists and there's something it points to. And so this is what we're going to do with this family. Again, it's not publicly exported because the implementation isn't safe, and then we don't want users to be able to manufacture their own proof of ownerships. All of the proofs of ownership should come through the combinators that we provide them, so that we know for a fact that they are valid proofs of ownership. So what can we own? We can own a slice of the region, essentially, that starts at a given index and ends at another index. And additionally, we will have this environment that we know the content of the region that we own. So here we have a list of bytes. And the way this is enforced is, as I said, you have a copy of the region, of the start and end points. And then you have this environment that the end should be the start plus the number of values that are stored in it. But as you can see, here there's no enforcement that the values we are claiming are in there actually match the content of the region. And that just because buffers are an abstract type, there's no way for us to insist statically that they have this content. So this is why we don't export the constructor. Users won't be able to manufacture these proofs. And then if we're careful about the way in which we design our library, the only way to come up with a proof of ownership with a given set of values will be to actually own that slice and actually have these values inside. Okay, so let's remove. Right, so the first thing we can do is we can try to allocate some memory. And if we do that, then we, given that the process succeeds because it's an effective operation, there might not be memory left on the computer or whatever. If that succeeds, then we should get a buffer of that size. And what's a dynamic buffer of that size? Well, it's something that you own with a new region that just came out of nowhere. That's what allocation does. That starts at 0, ends at the size you passed, and then has some arbitrary content And this content is marked as runtime irrelevant, meaning that it's essentially postulated here, but because you don't get to inspect it to make runtime relevant decisions, it doesn't matter. So all of these things are marked 0 here, are erased during compilation. So even though it looks like we have these postulates in the program, during compilation they will go away, and then things will just so that's 2. Then what do we have? Oops, okay, so then one of the operations we can do, if we own a region of the memory, and we know that it is that it can be decomposed into 2 sub-regions that are next to each other, we can decide to split it, and this will destroy the proof of ownership for the wider region, and this will create 2 proofs of ownership for the 2 sub-regions. So here you can see I own a region that starts at start and ends at end, and it looks like a list of values appended with another list of values. Its content looks like that. And so I can take it apart and get a linear pair. So all of these things are linear. This implication here is linear, which models the fact that it is consumed. And I get a region from the start to the start plus the length of these that contains these, and then another region from the start, from the end of the first, actually, to the end of the overall buffer that contains the W's that are left afterwards. And as you can see, the implementation is just propagating around the same buffer. Because essentially what we're doing is that we're owning slices of the buffer, so we don't need to duplicate the data, we don't need to move it around. It's just passing a reference in effectively to the name of that region. To 2 things. And so the linearity here, it's a bit annoying because what we really want to talk about, in a sense, is uniqueness, right? We want to say that these proofs of ownership that we have, meaning that we can act on the region, are unique. And therefore, if we make a modification locally, other people can work on their own slices of the buffer, and they will never interact. But there's no way to talk about uniqueness in Idris, so the only way we can enforce it is by having linear resources that we are very carefully not duplicating. And we are only providing combinators that will respect this invariant that the ownership proofs are unique, non-overlapping, essentially. Okay, so we can split things. Can we put them back together? Yeah, so if for the same region, we own the first slice and the second slice, and they happen to be side by side, we can just group them into a bigger one that contains the whole content. So that's the opposite of splitting. And as I said, we don't have decided on equality on the region names, but when you create a region, it's a static looking sort of name. And then it is unique, but through unification, you can notice that things are talking about the same region. So that's how you get to combine these things. Yeah, this is more of this. We can throw away a proof of ownership because I mean there's no reason to be forced to use it. So in this case, I mean the buffers are garbage collectors, so we don't free anything. It's very easy. Plus here we wouldn't want to free because for all we know, it's not the full slice, so that could be problematic. And then we can start implementing some primitives that will actually allow us to look at the content of the buffer. And this is what this is doing. So if you happen to own a region that starts and then, that doesn't matter, and contains some values these, then providing that you're using an index that is somewhere in these. So this is what this thing is saying. Notice that this is erased too. So at runtime, we're just looking for the index. We're not talking about the proof that it's a valid one. What we get back is the proof that we still own the slice because it was consumed by this function, together with a singleton type, which tells us that we get a runtime value that corresponds to whatever the singleton is indexed by. So we'll get a byte, which corresponds to the byte that's actually at index IDX in these. And so that's essentially reading from the buffer, but in a way that reflects the value that we get at runtime into the with respect to the indices. So in a way, this is a bit like this. Here we get back a value, and then we also get a proof that it is equal to whatever was stored in memory. So this is exactly what this is encoding. And we still have the information. Then we can also set values somewhere. So it's essentially the same logic, right? If you own a slice of the buffer and the index is in scope, well, is in range for that slice, then you can set a specific byte somewhere in the buffer. And what you get back is the ownership of the buffer, but now we need to update the index because the content has been updated by setting exactly this value. So we do have some proofs here, but they're all about like this invariant and the length of the index is exactly the difference between start and end. So all of this will get erased at runtime essentially, and this will be equivalent to just setting the value and then returning the buffer.
So since all of this abstract, these proofs are for you.
Yeah.
Use them self-reflective, you could like not do proofs, right?
Yeah. We do use them sometimes, so it's something I skipped over. So this is using the proof. So if you ask for the length of the buffer, you're going to end up with the length of the list it's indexed by, which is what this is saying. But this is actually proven, so you could also postulate it, yeah. But then if you make a mistake somewhere,
yeah. No, so this is like the trusted form.
Yeah.
Right, but you're not fully trusted. So it's obviously written.
Yeah.
It's just the
yeah, it's so easy to forget a +1.
Plus also it's a hidden trusted core, right? Because you're not using the proofs at runtime, you're just erased. Then it's like, because what I'm not seeing here, and this is not bad from a critique, it's an observation or comment.
Yeah.
Is unless you want to operate all proofs at runtime, all them is like compile time. Just you look at what you're actually exposing, all these proofs are in either in where blocks or they don't get exported.
Oh yeah.
Yeah, used to that's good thing.
Yeah. Yeah, because I mean you don't want to be able to look at the implementation, that's for sure.
I suppose one thing is like this is the difference between building something that's truly verified system like your deepness and the shallowness just get rid of the non-operate on proofs.
Yeah, no, but here it's very important actually that you don't export the implementation, because you can see that here when I allocate a buffer, for instance, I'm postulating the values that will be the content of the buffer. I mean, in shade, it turns out that it's all zeros, but let's not build this into the library. And so here you get back what is essentially an existential type telling you there is, that's the region, there is some content in there. And if you were to allocate a public export, then you could actually notice that it's always the same postulate that's being fed as the content. And therefore, you could prove in theory that allocating two different buffers gives you exactly the same content at the start. And that's not something you want to be able to prove because we're not making any assumption about whether it's initialized or not. So yeah, it is crucial here that everything is just export, not public export. Yeah. Both the data types and also the functions. So you can set bits, and then we can start doing fun things like programming over these things. So the first one I have here is the type of map function over a buffer that you own. So if you take a function from byte to byte and you own a region, then you can update it in place and you will own the same region, but with the content updated by mapping the function for every entry. And then we have a bunch of lemmas because we need to manage the lists of stuff. And here is the implementation. It's not too bad. So, I mean, this is exactly what you'd expect, I guess. That's that you start mapping from the left-hand side and you go along, which means that and during the intermediate results, you've updated a prefix of the map, which has been mapped, of the list, which has been mapped over, and then you still have some work to do on the right-hand side. So, and this is what this loop is doing here. There are some invariants that are built in because reasons, but you can see that here you start with a prefix where you've already mapped the function and the rest of the thing you want to work on. And then eventually you will return a region where you've mapped F across the entire thing. And we're using snugness because they flow the right way when we are going.
Which the separating conjunction.
Where is this information conjunction? Well, it's implicit because all of these ownership proofs, as I said, are unique and non-overlapping by an invariant that's built into the library, which means that if you're operating on the bunch of memory and someone else is operating on a different bunch of memory, by construction, there's no sharing. So their ownership proofs are orthogonal to yours, which means you can combine the two programs.
Stuff you use internally with semantic.
No.
Your chunk of old memory.
No. No, so this is the
disposal of the.
no, so this is a sequential map.
Right, it's kind of used in get bit
Right, get bit say tells you that it is unique and you own it, and then set bit say also assumes that it is unique and you know the rightful order. I mean, this is it, right? It's the one here, plus all the invariants that mean that you were never able to duplicate it from the time you got it at the beginning, which guarantees that it's unique globally. But we don't have uniqueness.
The split you showed before, separate junction, the L pair.
Right. So here we take one proof and we return two proofs, talking about separate slices of the buffer. And if we look at L pair,
Yeah, I suppose the weird thing is,
it's
because the linearity used there and the implications was there. So that every pair in this is separated. In the interest is separated. But lots of things are implicitly banked. And when they're banked, they kind of don't much their resource and sensitive. And so it doesn't matter if they're separate.
Right, the natural number. For instance.
Yeah. Well, so yeah, when you curry, we're using separations of the arrow.
Oh, yeah, skip over it, but
Yeah, when you do the, when you do the join, it's used to put that together. Next to arguments.
yeah, we can take an L pair of arguments. Right.
I think there's certain things you can't. It's not exactly a bunch of applications to use the assertion logic, assertion, assertions and separation logic. I think there's some things you can't say. One of the can't say.
Maybe higher order things.
I think what about when you nest with products and separating products? But in theory, you can do a separation logic. I don't see any actual use. But you can have two things where you have two separate views of the same piece of
Okay.
but we're using the and, like I said,
No,
here I think you got to encode it using that.
that's a linear function from the domain.
Yeah.
Yes, it might be possible.
Yes.
It would be interesting to do actually. Yeah.
How much of that map, is it easy to see what's erased and what isn't?
I mean, everything that's marked 0 is erased, right? So you're reading, then you're observing that this is the identity, right? Reindex takes a proof of an identity and casts the thing. So this should go away. And then you're setting the value. You are again reindexing and then calling the loop. So you're reading, resetting immediately. That's what we're touching. So
Ratio of proof of structure as actual work.
yeah, so there's extra stuff here because, for instance, you could read that index IDX plus 0, and then you wouldn't have to rewrite by this, but you would have a useless plus 0 operation. I guess should get optimized for me. Who knows? But some of the reindexing is inevitable because you're reading any of this zipper structure and you're saying that I'm reading far enough that I'm just beyond the end of the bits I have already processed. And so this you need to prove, I think. Or you would need to pass the get bits thing in a higher order way so that you can have it every time.
It's a bit one line.
Right. Yeah, but you would be working in C.
You have a copy.
I mean, this is bound checked, right?
Sure.
So,
You have a copy and representation of labels.
no, they're just natural numbers.
Yes.
An index.
That's copy.
Yeah.
It's not, they're not treated as directly. They're automatic.
Oh, yeah, no, so there, yeah, okay, there's a bit of confusion. So the labels here are more like the regions, but then here in the example, they were just a single byte. But in practice, you could say I have a label that's for an array, and then you would index somewhere into it where you would say, I don't know, I'm looking at L5.
So they just don't know.
No,
The regions are.
the regions here are abstract.
They're actually-
Yeah. Okay, so then my initializing is just the same as my thing with constant function. I'm actually folding up with this. And then something that starts being even more interesting is that because we have this ability to chop up a given region into smaller regions, given that we have enough primitives to do parallel programming in Idris, we can start running some of these functions in parallel. So here I'm writing a little something that's parameterized by an implementation of map, and we'll give you another implementation of map. And what it does is that it grabs the length of the buffer, divides it by 2, and then splits the buffer into the 2 halves corresponding to, provided by this divide by 2 function. And then in parallel, I apply the map that was supplied to the left part of the region and to the right part of the region also. We get the results back, and then we can combine them using this append function that we saw earlier. And through a bit of reindexing, we can return the buffer where we have effectively mapped the function across all of the values. And then we can have some fun with iterating this one step of splitting the buffer into 2, and then at the leaves applying the sequential. And then that's where we end up with this thing where I don't know if I should run it. Was there a robot? I've updated it.
Mistake close quotation mark.
Right. And let's do something smaller because with Zoom and so on. Also, you can process 15 megabytes. Yeah, so that's the idea. So I have some basic things. I also have this fault map, and this one is a bit more interesting because if I can find this, now we're starting to say that this is only valid if you have a verified monument, whereas in the standard library or Idris you can write a fault map with any old monument, but because to compute the singleton by splitting the buffer into smaller things, you actually need to know that you can reassociate the operations. So it's necessary to have this constraint. And you can get your region back and also the result of running this function. One of the issues here is that the setup that I have means that powerful map here, it's again the iteration of this splitting, applying, and then combining back. When in practice, you probably want to split first, and then have a bunch of steps that are happening on the sub buffers, and only at the very end bring them back together into a big one. Over here, I don't know if it matters a lot because we never actually split the buffers, it's all pretend. But it would be nicer from a programming point of view to be able to describe these skeletons, these parallel skeletons directly as the composition of various steps.
Any questions?
Does it still compile the constructors for the open?
So it is automatically optimized the way all of the data types that have a single constructor and after erasure have a single field. So everything will be unboxed.
Right, the open will turn into
So the region will just be directly a buffer and then owned. Oh no, owned will be a record actually because I've packed these two in. Because it's a bit annoying to have to explicitly say, I only start at the end to be available for this operation.
okay.
When in practice, all the combinations that you have will recompute the start and the end for you. So this makes it possible to write like this function, which.
So is that in the map one? Is there a bit of extra packing and unpacking and packing the recurrence?
Here,
No, wait, the map position.
or the split hat.
No, just the map.
No.
Yeah. So when you get to the end of the loop, or to the end of the loop. But inside set it's 8.
Yeah.
That's it.
Yeah. Right, so if we are removing the proofs, then we could have an extra bit of magic to just pass the same thing again.
Because I wonder if in terms of what's actually happening in the generated code,
Yeah,
it's storing the facts, it's storing the start and ends.
Yeah.
And it's actually recomputing them as it does that. But it never checks against the facts. So I wonder,
I mean, you do use it in map, for instance. So in map,
yeah,
when you set the line first. Oh no, I made the IDX here, okay. So
No,
it's
we get-
initialized. Hmm.
starts at 0. Oh, because H is 0, then it's counting to. So it's getting the length of the buffer.
Yeah, so it is in get back. So there are most of the definitions. Yeah, so here we use the start plus the
Yeah.
offsets.
But I usually compile that loop as unpacking the code, get the 2 fields out,
Yeah,
doing nothing to putting back in, and making another code. And the garbage collector has that tidy up all of this.
yeah.
Really, they should really be unlocked.
Yeah, so maybe it is better to leave the start and the end on the outside.
Yeah.
Change that for sure.
How readable is the scheme change?
Well, I don't know, I don't even know that.
Probably it's not.
Yeah, usually.
Well,
No, that's the one that's part of the rectangle.
It's this happen.
Split that. Okay, let me move this here. So split that takes a bunch of arguments and then
I think if you recollect that.
yeah. I mean, we would need the
must be max fine to do this, but
right. So we're getting this make point of the same buffer for both of them, right? The start is the original start,
Yeah.
and the end of the first one is the original start plus the size of the thing we're taking.
So this is okay.
And
Stones in back.
yeah, well, this could be dead bounds. And this is E3. And oops. Oh yeah, but this is just the end, which was. Yeah, so this is the buffer, the start and the end extracted from the make group. But it could, yeah, it could be threaded implicitly, basically, like not storing them. Yeah, I've gone back and forth. At some point, I was also indexed by the size of the list, but it got in the way, so I moved it. There's definitely some leeway in how we move it. So do you know the Emacs micro?
That's a cube.
yeah, that also should be one. No, it's not fine.
Sorry, let's just put it.
I mean, we can see here, it's not too bad. We split that on 9. Where did it find this size to use? Oh no, there's a case. Oh, okay. Oh yeah, because okay, the pattern matching lets are elaborated in 2 cases. That's probably not ideal. Like they're becoming to auxiliary functions, right?
It looks like a
Yeah, so this is going to be the 2 halves of the length, right? Because then it's going to split out with E2, which will be the first half to the side of the. So yeah, definitely. So at the moment, I'm trying to write a initial proposal and looking at the generated code and trying to improve it. Very much part of it, although it's more long term than.
This is maybe just an interest question, I'm not sure, but in your code, there's a few places where you had like an L1 type constructor. What does that do?
Oh yeah. So it's a technical thing. So now can you So. So this linear IO thing actually allows you to combine IO operations with linear values. And so you can say that some IO operations are linear in the argument and so on.
Mhm.
And what this is saying is that whatever we return, we only have one copy. Whereas if you use the L without restriction, then you are allowed to duplicate the results. And there's also an L0 where you return something that just is there at compile time for invariant traffic that will not be available at runtime. And this might be another source of potentially inefficiencies in that these L1 things, they are essentially a tree, a deeply embedded tree of IO actions. And then that's why in the main we call this run function, which turns the explicit tree into an actual set of IO calls. So long term, it might be necessary to do this. And this is just in the Sun library space.
Any more questions before we finish up? Okay, then let's thank you again. And as I said earlier, this was our last scheduled 101. So if anyone else wants to propose a talk, put something in Zilla or email someone, I guess. Okay. Bye, everyone.